Hi everyone, I'm Agastya, computer science grad student, and today I am attempting to use an LLM as a CPU. So, looking at this problem, a CPU is a deterministic machine, whereas an LLM is probabilistic and differentiable. However, I am trying to stimulate the von Neumann cycle on an LLM using an LLM and try to make it act deterministically to fetch instructions, decode them, and execute them. And I'm going to then try this setup on a couple of problems. Like here, I tried to make it resolve the errors in a file not compiling, and it resolved it within a couple of clock cycles. Okay, so let's get started here. And I use UV for package managers because it's much better than Ollama. Sorry, not Ollama. It's much better than pip. And the LLMs I'm going to use, I'm going to access them via Ollama. I already have Ollama installed in my system. To install it, it is very simple. You can just install the app and then everything gets configured automatically. You can then use it in PowerShell also. And what I installed here was the Python package for Ollama. And also the model I'm using Kimi K 2.5 Cloud, which is the best reasoning model among the models available there. It's also fast enough. It has 50 tokens per second latency. Also, even the free tier of Ollama provides enough credits to build the system functionally. Now let's create a file peripherals for my CPU. So let me show you how my CPU is going to work. So when I start my CPU, so this registers, RAM, they are, I'm just like in practice, these are just going to be some data types, but that represent the actual register and RAM. And then, so you would need a peripheral to run the file whose code we are going to be fixing. So this file is just for the purpose of that. And okay, that is just a fast way of writing this file. And if we look at the code, execute ALU, so it is for executing the function, and I'm naming it as ALU. This is this function, and this flag in the dictionary maps to this function. And then writing into the data into the registers and RAM, which we initialize in the main file. This function is doing that, a simple F file file writing in Python. And this here you can see using subprocess in Python. I am running this Python app.py, so I'll be making an app.py which will contain all the faulty code and which will not compile, and then our CPU, our neural CPU, will not just repeatedly execute this file but also solve the errors in this file, and capturing the output of this execution and then trying it after a little bit of timeout. So, and then this function will return the result.stdout. This is the feature of this process that we are using here. And otherwise, if it's giving us any errors, then we are storing them in the ALU fault. And okay, so yeah, these are the two variables that are getting returned, ALU return and ALU fault. So these two functions are here in the peripherals. Now Now let's move on to the may to a set of prompts, and the prompts that I'm giving to my LLM, that will define the instruction set architecture of our CPU. So I will create a prompts file, and I'm trying to define a 16-bit virtual Harvard architecture, and we are going to give AI specific registers. It will have a program counter R0, R1, and R2 for general purpose registers for math and logic, and a RAM. And it's just a memory bank to store the data between cycles. So by ensuring that these specific set of registers and the specific values are there, and these are being passed as context to the LLM in the next cycle of generation. So we are grounding the context here to prevent hallucination, and it is representing how actual data is being managed by our LLM CPU. This is the prompts file that I'm creating here. So system ISA is what I'm just calling this prompt. And okay, K25 just means KME 2.5 that I'm using for architecture, and the registers, and as I described, some flags. So if an instruction has been completed and run successfully, then it will run a halt, and then just a memory map for the memory ALU output. So we can see that this is being simulated as an actual CPU, not an actual hardware that I'm implementing. But yeah, this is just a simulation of the CPU, but it's exactly like what ZSIM does, but this is our neural CPU. So again, an output format. So see, this is a system prompt that I have defined, which is very clear. This is giving an output in a strict JSON format, a thought which the LLM saw whatever happened. Our CPU saw whatever happened in the execution of a system, and what did it think, what was its response, and then it updates these data values. See how the CPU is doing a write back in the memory. So yes, the program counter is being updated, R0 values, R1, R2 values are being updated, and if any halt has to happen, so it will throw in the flag for that. And then this the patch, which it will I think it's for generating the patch. Yeah. Okay, so moving on, I have to implement a kernel for the CPU to operate. And right now we have implemented the peripherals of our CPU, and the how it's handling the internal data, and what the output it is giving. Now a kernel to run the loop of fetch, decode, and execute, and run the clock cycles. So I'm going to use this kernel.py that was created. And yeah, in this one we are using the peripherals. So we took our system call map, or the system call map defined here. So the system call map is just a simple way to access these two functions that we defined in our peripheral. And then the system ISA, the instruction architecture, so sorry, the instruction set, which is right here, our ISA. This is what we are giving into the kernel. Let's see. And just looking over the code, we are initializing the hardware state, and the memory is empty. These are how the registers are going to be initialized. And so this is for the testing part. So I'm intentionally writing a broken code here. So this using write feature of Python file handling. I'm making a app.py, and inside it I'm writing the broken code. So this is a function to calculate the area pi r square, area of a circle, and then calculate area with radius 5. Now the problem here is the 2, which is the exponential power of the radius in the area of the circle. I'm passing it as a string and not as an integer, so it should throw in errors. And this function is defining the kernel cycle, fetching the status from ALU. So system call map execute the ALU instruction, recursing back to our peripherals. You can see the syscall map that gives access to these two functions, and executing ALU right here is mapping to this function, and inside my clock cycle I am referring to this exact key, which and then square adding these brackets. Basically I'm calling this function. You can see this key maps to this key maps to this function name, and then calling this function. And what this function does, it will run that faulty file and get the output and return that output, which is our ALU status. So the clock cycle is fetching the ALU status, and if ALU return in ALU status, then target state reached. So this is how I am knowing that the function which we executed last, it ran successfully, and ALU return we are setting in that executing function right here. If result code is return code is equal to 0, return code 0 means file ran successfully, and then if this is in the result, then we say the halt state is reached and execution can stop. Otherwise it will give me an ALU fault, and I will give that ALU fault to my LLM, and then it will see what fault happened in the previous instruction and try to solve it. So this is the prompt that I give to my Ollama chat model. So ALU status is this, and right now my register files are these. The RAM bank is this, and I'm giving it a system ISA, which is this is typical in agentic coding. You give a system prompt and append to it another prompt. So typical system ISA, I'm giving it the instruction. Okay, so this is the Ollama model. I'm telling it, hey, so this is the instruction set architecture, and then the prompt that I'm giving is explaining the current status of the registers and the current status of the last execution. And then my Ollama, just reading this prompt, just by reading this particular prompt, you can see I did not add any other English language things like, hey, you are a neural execution, whatever, something like that right now. And it will just, right now the LLM is just getting access to the instruction set architecture and these values of the registers which are being updated with every single cycle, and then it is expected to return this JSON format with the updated values of the registers and memory, everything, and then it also sees how the last instruction happened. It's writing. And yeah, so this was the instruction decode part. Execute part, this is the response that we get from our LLM. We just split it into different lines, and the JSON, we're just loading it in a JSON object, that is the microcode. And from this microcode, I'm extracting the thought which was what the LLM saw. And the DMA write this patch which the LLM gave me. I am giving this patch using my syscall, which is again in my peripherals, the second function in my peripheral, which is enabling me to write into a file using simple file handling in Python. And this is the file name, and this is the patch that my LLM gave me. And then I update the new registers again from the JSON format memory, and I just output, okay, this is the update in the register and the update in RAM states here. And then I, yeah, I this function is returning the new registers which are being set in the main loop. Okay, I will have all of this code uh, open sourced, and you can read over it. It is pretty simple to understand. And yeah, at the last, I am just running my kernel, and it's a until we reach a halt, and the and I'm running it just for five register cycles to make sure that the system does not keep on going. So just running for 5 cycles. That's just a limitation I enabled here. And then yeah, when it stops, CPU halted, system shut down. Okay, cool. Everything is set, and when I run this kernel.py, it will main.py, it will write this faulty code, and then it will start our LLM CPU to execute this code, run this code, and keep running it if until it runs successfully, and if it breaks, then it will just correct it. Now that everything is set, let me just run it. See it initialized here, clock cycle 0, we hit an error, and now okay, that was the LLM start, and it stored R into 2 in one register, R1 is by 2, and R2 type fix. Okay, what it's gonna do. And in clock cycle 1, again we hit a fault, and the LM says indicate syntax error at PC1, return no code. So violation instruction stream attempted to execute, return without stack frame. Analysis of register file shows R0 holds valid operator, R1 holds exponent value but missing register dump, R0, okay, and R2, okay, and fixed. See, so it's fixed all everything, and oops, if I look at my app.py, you see, it's fixed now, and it ran perfectly. So this was a simple simulation of using an LLM as a CPU, and this proves that we can interact with an LLM in a slightly more deterministic manner, and we built a self-healing loop that managed its own memory, fixed its own bugs, and itself down it shut itself down when the job was finished. Okay, so I think this was pretty much it for this video. I tried to implement an LLM as a CPU to use it in a slightly more deterministic manner and simulate the one human cycle on it, and then use it for a task of running a file, fetching data from the file, and if the file did not run correctly, then continuously change in it and make it run correctly. So in later on videos, I will try to test this thing with more complicated set of problems and expand this further. So if you're interested in that, you can keep a check. And I also created a much more detailed video using Notebook LLM about this entire problem of an AI operating system. So you can also look at it, and you will have much better context about this problem of using LLMs as an AI powered operating system. So thank you for watching.